Hello students, welcome to the concept explanation of hybrid pi common emitter transistor model components. In this video, I am going to explain all the components of common emitter hybrid pi transistor model. You all know this is the hybrid pi transistor model. For what? It is for the transistor which is acting as CA amplifier. You know the CA amplifier circuit. At high frequencies, all the capacitors get shorted. Input capacitor CB, that is a blocking capacitor, output capacitor, coupling capacitor, and the emitter bypass capacitor. If all these get shorted, then RE becomes short. And as this is short, yes, you have a supply here. Yes. So now here you have another short. This short is because of the capacitor CBE. And there is another short that is because of the capacitor CBC. You know very well about this circuit. I explained in the last video. So at high frequencies, so this input blocking capacitor and output coupling capacitor and this emitter bypass capacitor has no effect. Okay, because yes, as it is, this Vs will go like this, but the effect is only because of the CBC and this CBE, because when these are short circuited, output becomes 0. So that is the reason you have to take care of these two. This is CBE and this is CBC. Okay, so now this model is completely, see this is base and this is emitter and this is collector. This circuit is only the circuit of the transistor, the internal circuit of the transistor. Means this is the internal circuit of the transistor, which consists of collector, base and emitter. All other components are external. Okay. So this circuit is only the internal transistor circuit. Means the base collector and the emitter circuit. All other external resistors like R1, R2, RC, you have to connect in the circuit. Okay. Suppose if I want to connect when you're going for AC analysis, you have to make the DC signal is equal to 0. We know it. We have to make the DC signal is equal to 0. When it is 0, R1 and R2 comes in parallel and the end is at base and the other end is at ground. So you have to keep here. Yes, here you have to keep the two resistors like this, R1 and R2. Okay, here from the collector to the ground you have to keep another resistor called RC, because this RC also goes to the ground. This is the circuit. These are the external resistors, and this total part up to this, from this to this total part is the part of internal circuit. The total part is internal circuit of the transistor, remember. Okay, all other external connections you have to connect to this equivalent model. Okay, so now I'll explain about all these components. Even the H parameter model also, H parameter model is the equivalent circuit of the transistor only. The external resistors you have to connect external to the equivalent circuit, that is H parameter equivalent circuit. Okay, I think you understand. Now I'll explain each component. I'll start with RBB dash. What is RBB dash? RBB dash is called base spreading resistance. Okay. What is this base spreading resistance? Why you have not seen this RBB dash in the case of H parameter model? I'll explain. See, what about the transistor schematic diagram? This is a transistor schematic diagram. This is emitter, this is base, and this is collector. Emitter terminal is here, base terminal is here, and collector terminal is here. Okay. We know when you apply the base current, see high frequency, this is hybrid pi common emitter transistor model, we are using it for high frequencies. Okay, when the signal, high frequency signal is going, or you connect the connected base, you know you are connecting the input between base and emitter. When you connected the base, is the carriers first go like this. The carriers first go laterally in the base and then goes to the emitter base junction. This is emitter base junction. And this is collector base junction. Okay. To reach this center base junction, carriers has to travel laterally in the base and then reach to the emitter base junction. In this path, as this is a semiconductor, base is semiconductor, there exists a resistance called RBB dash. Okay. So we are not, the carriers are not going directly to the emitter base junction. These are traveling to the base and then laterally into the base and then reaching the emitter base junction. So between this to this, actually we are saying this as B, but here this part, this total part is again, to reach this, the carriers has to travel this part. Okay, this resistance between this and this emitter base junction is called the RBB dash. Now this terminal becomes, this is B and this is B dash, this terminal becomes B dash. Actually where the carriers are meeting the emitter base junction is called B dash. Okay, the external terminal is B and the internal terminal at which the carriers are reaching the emitter base junction is called B dash. The distance between, or the resistance between B and B dash, means the things are like this. See here, this is B and this is B dash. Okay, here this is the transistor. The carriers will go to the junction like this. So this is the distance. This resistance is called RBB dash. Fine. That resistance spreaded in that extended base is called base spreading resistance. Yes, the question is why we are not considering the RBB dash in case of low frequency analysis. That is when you are going for H parameter model analysis. See, when you are going for H parameter model analysis, we know all the capacitors are open circuited. Means yes, all the capacitors are open circuited, means blocking capacitor CB, coupling capacitor CC, bypass capacitor CE, all are open, and also the capacitors, the junction capacitors CBA and CBC, both are open. Okay, totally 5 capacitors are open. Okay, nothing is there as this is open. Junction capacitors are open. No one is there to stop any current or voltage going into the transistor at the junctions, because all the two junction capacitors are open. Okay, I'll explain here. Yes, here there exists a junction capacitor, but that is open. Here there exists a junction capacitor that is also open. So these junction capacitors are not doing anything, are not affecting the transistor. Okay, these are just idle. Means you can say the capacitor is open, means it is not doing anything. So yes, whatever may be the signal that you are giving from this side, it is going to the base and then to the emitter. Okay, so that is the reason we are not yes, taking any considerations of these junction capacitors. But in the case of high frequency, you are taking the junction capacitors only. You are taking only the junction capacitors. So when you are considering the junction capacitors, why you are considering the junction capacitors? Because junction capacitors are stopping the signal to reach the base of the transistor. That is the reason the output becomes 0. Okay, fine. Then if suppose there, yes, if you are considering the capacitors CB-E and CB-C. Okay, you know, to operate any capacitor, it operates with a time constant, means it needs the help of resistor. Yes, in the case of low frequency, we don't have any capacitor operations here, charging and discharging concept. That is the reason we didn't take the help of any resistor. But in the case of high frequency analysis, so here you have the two capacitors CB-C and CB-E. Okay, so to CB-E to act or CB-E to do something, it needs a resistor. Okay, that resistance here is, we are calling it as RBB dash. Okay, and here that CB-C also, for CB-C also, the resistor RB-C is helping to charge or discharge. So here CB-C. Here the resistance between the base and emitter, that is RBB dash, is supporting the CB-C. Then only CB-C can act. Means all the capacitors will take some, depends on some time constant. Time constant of the capacitor is RC, R into C. So where is the resistance for this capacitor to act? So now this RBB dash comes into picture. But it is there in the low frequency also, but there the capacitor CB-C is not there. That is the reason it is not considered, and the second point is the value is very less. But this for the CB dash C also, that is by the help is by the RB dash C resistor. Okay, I think you understand the need of RBB dash. RBB dash is an the order of 100 ohms. Okay, very, very less. Okay, coming to the next elements, CB dash C and CB dash E. The CB dash C is the transition capacitance. The CB dash E is diffusion capacitance. You know, when the transistor is an active region, emitter base junction is forward biased and collector base junction is reverse biased. That is the reason the junctions possess some capacitance called diffusion capacitance and transition capacitance. Coming to the component RB dash E. It is the forward bias resistance between spreaded base. RB dash E is the forward bias resistance between spreaded base B dash and the emitter E. I already explained. This is emitter, this is base, this is collector. The external base terminal is generally we will call it as B. Carriers has to travel laterally for some distance. Let the terminal be B dash. Okay, so from this B dash to the emitter, the carriers has to travel like this. So this resistance between B dash to E is called RB dash E, and the resistance between this B and B dash is called RBB dash. Okay, so the resistance between B dash and this emitter junction is called RB dash E, and the resistance between B and B dash is RBB dash. Okay, so this RB dash E is nothing but forward bias resistance. The RB dash E value is around 1 kilo ohm. It is around 1 kilo ohm. Okay, so totally, yes, if you see the circuit, yes, I can say this is the input side, this is the input side. Okay, so what is totally the input resistance? The input resistance RIN, total input resistance RIN can be written as, yes, sum of resistance RBB dash and RB dash E. Okay, so that is about the RB dash E. Now coming to RB dash C. In the transistor circuit, this is emitter, this is base, and this is collector. This is called base collector junction, and this is called emitter base junction. Okay, and suppose if it is NPN transistor, the connection is like this, so it must be reverse biased and it must be forward biased. Okay, so when the base collector junction gets reverse biased, you know, the depletion region width across the base junction increases. The depletion width is increasing, the base carriers will move towards emitter. Okay, so the emitter current will increase. That emitter current which is increased again will increase the collector current. This is called feedback action. What is happening? Because of this base width, because of the depletion width due to this supply, negative supply, the depletion width at the base collector junction increases, which decreases the base width. You know the concept, I think you have studied in EDC, that is called base width modulation. Okay, so base width modulation is the concept of change in base with respect to the applied reverse voltage. As the base width decreases, means the base is pushing into the emitter, means the base carriers are going into the emitter, which will increase the emitter current. That further increase in emitter current will increase the collector current. Okay, so what is happening? The thing is going, actually the phenomena is going like this. Again from the emitter it is going like this. Okay, fine. Again the collector current is increasing, means this is called feedback. Okay, so to include this feedback concept between input and output, we are including a small resistance called RB dash C between B dash and C. Okay, so that is the resistance RB dash C. RB dash C is to indicate the feedback connection between, yes, actually what is meant by feedback? There must be a connection between output and input. From the output to the input. Actually, input to output connection is common, but if the connection is between output to input, in what way it is connecting to the input? See, emitter, yes, this reverse bias is changing the depletion width, means increasing the depletion width. The depletion width decreases the base width because the depletion width is penetrating more into the base, and the base carriers will move towards emitter, which increases emitter current. Fine, that emitter current again increases the collector current. Okay, so this is called feedback concept. To include this feedback concept, yes, you must indicate it by a component. That component is RB-C. Along with this role of RB-C, I already explained RB-C acts or it helps CB-C to discharge or to charge. Okay, then another component is, yes, the transconductance GM. Yes, this VB-E is the input current. You know, yes, you'll get VB-E because of this application of your input voltage. Okay, so that VB-E is creating a current, base current. This base current will create a collector current because IC is equal to beta IB, we know. Okay, so means this IB is depending on, means this IC is depending on IB, which is depending on VB-E. So that is the reason the output current is a dependent current which is depending on VB-E. So to keep that dependency, here we are using a dependent current source. So that is GM VB-E. This justifies the inclusion of current generator IC which is equal to GM VB-E across collector and emitter. Okay, so I'll explain. This VB-E is the input voltage which creates input current. This input current will create the output current IC because IC is equal to beta IB. So this IC depends on IB which is depending on VB-E, means IC is depending on VB-E. So to justify it in the output side, you have to include a dependent current source of value GM VB-E. Okay. And then coming to the output resistance. Output resistance RCE is the resistance between the collector emitter due to the flow of transistor current. Okay, it is generally output resistance. It is the output resistance between the collector and emitter. Okay, here it is. This is RCE. It is a resistance between collector and emitter. Okay, so I think I covered all the components. Another point, RB-C is feedback resistance and CB-C is called feedback capacitance because it is in parallel with the RB-C is in parallel with the CB-C. That is the reason. Yes, this CB-C is also called feedback capacitance. Okay, so I think I covered all the components. Okay, and in future, I'll see all the when we speak about this hybrid pi model, we'll speak about hybrid pi conductances, not the resistances. See, here I explained all the resistances, but in future classes I'll explain like conductances. I think you know the difference between resistance and conductance. Conductance is equal to 1 by resistance. Okay, when you analyze the circuit, suppose if the circuit is a series circuit, it is better to analyze by taking the resistances. Okay, but if the circuit is parallel, like this hybrid pi, all these are parallel combinations. So to analyze this, because this is parallel combination, it is better to analyze using the conductances. Okay. So in the next video, I'll explain the derivation of all these components. Okay, thank you very much.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.